All right. Hi, everyone. Good morning, good afternoon, good evening. Welcome to today's webinar, Beyond the 2% Default, introducing PVRADAR's soiling loss integration within PlantPredict. Thanks so much for joining. We appreciate you being here. And let's go ahead and get rolling. I'll turn on my camera here. I'm Jason Spokes. I'm the Senior Product Director of PlantPredict at Terabase Energy. I'm joining you guys today from Los Angeles, California, and I'm joined by Tor Mueller, the CEO of PVRADAR, who's joining us from Munich, Germany. I am going to go through the agenda today and cover a very introductory slide about Terabase and PlantPredict, and then I'm going to hand it over to Tor to introduce himself and tell you a little bit about PVRADAR and why soiling matters to large-scale solar projects. I'm going to take it back over to run through a quick demo to show you how you can access PVRADAR data and the integration within PlantPredict. And then Tor is really going to handle most of the technical meat of today's webinar and go into a deep dive on soiling. So he'll cover the primary factors that drive soiling losses, and that includes PVRADAR's physical soiling model and the historical data sets that it uses, the model accuracy, validation, and comparisons to other models, and then, of course, panel cleaning strategies and optimization approaches. And he'll cover some of the additional PVRADAR products and services that can be accessed outside of PlantPredict. So we'll both come together for some closing remarks and announcements, and then we'll reserve some time for some Q&A at the end. And just a reminder that even if we don't get to your Q&A question live, we will be responding to all Q&A questions that are submitted via email. So we'll get back to you on any questions within the next couple of days. All right. So let's get going here. So for those of you who are not familiar with Terabase Energy, we're a Berkeley, California-based startup founded in 2019. We're building digital and physical solutions to help accelerate the deployment of solar, and that's what you see on the screen here. On the left, we have our engineering software and services for the development and pre-construction phases of the project. Central to that is PlantPredict, our solar energy modeling application, and that will be the focus of today's webinar. We also have construction products and services, including construction management and QC software that's active on more than 10 gigawatts of projects today. For the physical world, we've built a construction automation solution, Terafab. We basically bring a mobile factory to your project site, complete with an assembly line and rovers to automate the module to torque tube to pile assembly. To date, we've completed more than 40 megawatts of automated installation as we begin scaling that product commercially. And finally, we have our plant controls team that provides a full set of SCADA and power plant control services, including hybrid control systems. Diving deeper into PlantPredict and the PlantPredict suite, we have several cloud-based software applications designed for the development, preliminary design, and pre-construction phases of utility-scale solar projects. This suite has been used to analyze more than 1 terawatt of projects in the last year. This is 1 terawatt of unique projects, and we're extremely proud of that milestone as we see the PlantPredict suite being adopted by more and more companies around the world. Our core product is PlantPredict, which is an industry-leading energy performance model in the backdrop of today's webinar, and is the product that we've integrated the PVRADAR integration into. We have several additional applications which can be bundled with PlantPredict at our Pro and Enterprise license tiers. Design Pro is an all-in-one tool for design automation, material and cost estimation, and financial modeling that facilitates batch analysis for design optimization. Voltage Pro is our string length maximization application, and Terrain Pro is our grading design automation application for racking systems, and that includes terrain following trackers. We will be releasing an advanced site level 3D shade model next week. I'll be giving more details about that at the end of today's webinar. And finally, we have a CAD-friendly version of Terrain Pro, which can be used for earthwork analysis during the detailed design and construction phases of the project. All of our product tiers and pricing information are published and are completely transparent and can be found by visiting plantpredict.com. And with that, I'm going to hand it over to Tor and give him an opportunity to introduce himself and PVRADAR.
Oh, thank you, Jason. Yeah, my name is Tore Müller. I'm the CEO of PVRADAR Labs. We are a software and consultancy company from Munich, Germany. And yeah, PVRADAR was founded about 2 years ago by my colleague Franco Clandestino and I, who have previously worked at a large European IPP, where we have been tasked of assessing soiling losses, conducting soiling measurement campaigns, and optimizing cleaning strategies for new development projects, often using Excel. And unsatisfied with that situation, we decided to leave the company and team up with a team of Konstantin Pogorlov and a very experienced software developer, and started creating PVRADAR, which I will be presenting today. We have always kept a very close connection to research, and we're very proud that our team of advisors counts some very experienced people. And we're also happy to, for example, be part of the PDPS program of the International Energy Agency, working on the report of the optimization of power plants for hot and dry climates. Next slide, please. Already today, PVRADAR offers a variety of solutions. We have, for example, our web application, which allows project developers in the very early stage of the project to simply click on a map and model soiling losses based on historic data, get their soiling loss factors that they use for their yield estimation, then compare different cleaning systems and try to find the optimal cleaning strategy, and finally generate reports. This is the front end of our simulation engine. There's a different access to the simulation engine, which is through the API, which is, let's say, the star of the presentation today, which allows access to, for example, P50 monthly soiling loss factors, which is what you're calling when you're using the integration in PlantPredict. And then we're also working on a Python library, which for, let's say, the more technical users that have data maybe, and they would like to create their own models or fine-tune models for their sites. There's a bunch of tools that allows them to get data for these models, run them very effectively, and then share the results within their organization. But more on that in a few minutes. Thank you.
All right, thank you. And with that, we're going to bring up our first poll question, which should be live now. How do you currently estimate future soiling losses for your PV project? And I'll give folks a few minutes to respond. I see some responses coming in now. While that's going, I will turn off my camera for the remainder of the presentation.
I already see some interesting results. For example, the
Yeah.
validation of our assumption that, the title of the webinar saying that 2% is what's currently being used, and the poll seems to be validating that.
Yep, exactly. Yeah, so we're seeing, most people are assuming a fixed yearly percentage. We also see about 25% of people modeling soiling losses using PV or similar. Yep. Okay. Well, thanks for responding. And with that, we're going to step into let me go back. We're going to step into the demo portion of today's webinar, which is going to be in PlantPredict. So what I'm showing here is PlantPredict. And right now I'm in my project library, and I filtered my project library for PVRADAR, and you can see that I've already pre-created 2 PVRADAR projects, one in Florida and one in Southern California. I'm going to go through the process of pulling in soiling data into both of these projects. And I've picked Florida and Southern California for a good reason. Florida has a more regular rain pattern, whereas Southern California has kind of a rainy season and a dry season. So we'll definitely see some differences in soiling losses from month to month comparing these 2 projects. So let's start with let's start with Florida. I'll step into the project. I've already got a prediction created, soiling test. I'll step into that. And we get to soiling loss data from the environmental conditions weather data page. So I'll step into that. This is where we can select the weather file, and it's also where we can enter soiling loss data. Now in PlantPredict, you can enter soiling loss data one of 2 ways. You can either enter monthly soiling losses here, or you can also enter it via the weather file. So if you have time step by time step soiling loss data, it is possible to use that through the weather file. In this case, we're just going to use the monthly override. And by default, the prediction has 2% soiling losses. What's new is the import PVRADAR button down here. And this is live as of, I think, a few weeks ago. And this is where, if we click on this, we can start to pull in that soiling loss data directly from PVRADAR. When we click on the button, you'll notice that there's a couple of racking configuration related inputs. So we can select between fixed tilt and tracker. And if we select fixed tilt, we of course have to define the fixed tilt angle. If we select tracker, we get a max rotation angle and a night stow angle. And the PVRADAR model is using this information along with the project latitude and longitude in order to determine the monthly soiling losses. So what I'm going to do is I'm going to sort of keep these defaults. I'm going to hit continue. And what's happening now is we're sending that information over to PVRADAR, and we just got the response back. And you can see that the monthly soiling losses have been populated. Pretty low soiling losses, all below 1%. It looks like March is the highest month with 0.7%. Okay, so let's, by contrast, take a look at the Southern California project. I'll hop into the soiling test here, prediction, again, the weather page. Let's go through the process again. I'll keep the defaults, and let's pull in the data for Southern California. And you can see that in the rainier months, we have relatively low soiling losses, and then they really start to build in the summer months up to October, where we have over 7% loss, 7.2% loss. And just for illustrative purposes, let's say that we were to modify the night stow angle to, I don't know, 20 degrees. Let's hit continue. And let's just see if that changes the results. And it does change the results. October used to be at 7.2, now it's at 6.7. So an inclined night stow angle seems to bring down the soiling losses a little bit, which is interesting, and a topic that I'm sure that Tor will cover later on as part of his presentation. Last but not least, I want to mention that there is a link here to the PVRADAR documentation. So there's a lot of information about the PVRADAR model that you can read further on. And a lot of that is also going to be covered by Tor here in just a minute. So. Okay, so I think that covers let's go back to the slide deck, go into presentation mode here, and we're ready for poll question number 2. Who should be responsible for defining a cleaning strategy? And I see some poll responses coming in. Interestingly, there's looks like there's a heavy, kind of a heavy contingent for kind of later in the project lifecycle, either during O&M or during operation.
Yeah, it seems so. Although I will make a point now, I would rather start early, but I will cover that in a minute.
All right, so those are our results. So project development, 21%, EPC and investor somewhere around 10% each, and then O&M 31%, asset management 29%. So that's interesting. Okay, so at this point, I'm going to hand over the controls to Tor. So let me I'll give you the presentation access, and you are now the presenter, Tor. Take it away.
Perfect. Thank you, Jason. All right. So what I would like to show you today, is how our models work and how they can be used to determine soiling losses for a new site, and then also trying to reduce them in a cost-effective way through cleaning. But just as a motivation, or just to bring everybody on the same page, so let's assume we are building a new project near Yuma, Arizona, and we're a project developer, and we are currently doing the yield estimation, and we're asking ourselves what soiling loss factors to consider. And then maybe we ourselves or our colleagues from O&M are trying to think and determine a budget for the financial model of the project. And in that, they have to define a budget for a cleaning strategy. And we're trying to answer that. So what are our options? So the first thing we could do is we could try to look into literature and try to find if there's any clear answer given. But very likely we will find that, especially for the location we're looking at, there is no data available. So that doesn't really work. Second, what we could do is we could conduct a soiling measurement campaign in order to at least determine the soiling losses of the site. That may work, but is very expensive, and also very often for development nowadays, there you just simply don't have months and months of time to install sensors, wait till the results come in to draw your conclusions. So you need something that works faster and before that. So what many people are left with as an option is this kind of guesstimates that could, for example, be just assuming 2%, because I don't know, the PDSys once said that in their help section, or maybe have a little bit more elaborate guess, but in the end, it remains a guess. So this, I think, is what currently mostly being done, and the poll somewhat confirmed that. And what I would like to advocate or show you is that there is a better way of doing at this point in time, which is modeling soiling with physical models based on historic satellite data, which is both accurate and readily available. So how does that work? So this is exactly what you would be doing when clicking the button import PVRADAR in PlantPredict. And when you do that for a new location, there is a chain of a modeling chain that is being kicked off. And let's have a look how that works. So the first step of our model, of this modeling chain, is we start from the particle concentration, the concentration of particles at the very location. Our main source of data is MARA2. It's a satellite program that allows you to download, or that it contains data for the concentration of particles, different particles, for locations worldwide. Inside that data set, there is different types of dusts, sea salt, organic matter. You see the concentration of these particles in the first plot above for the year 2021. Our models are based on usually several years, 5 to 20, depending on the configuration. But it's a multi-year data set that we're working on. You're showing 1 year. What you could be doing now, and which is maybe familiar to more of you, is grouping these particles by their diameter to create a PM2.5 and PM10 time series. PM2.5 simply meaning all particles with a diameter of less or equal than 2.5 micrometers, and PM10 analog. Right. So our main source of data is MARA2, and it can be used to produce PM2.5 and PM10. However, our models work with the base data set directly. There are many sources of soiling. So dust is one. Then we have snow, which we have pollen, and these are, let's say, the more macro scale stressors or influences that you can model quite well. So our model already works so in regions where dust soiling is the primary source of soiling, our models work very well. In our platform, it's also possible to include snow modeling, but this isn't part of the API. And then what we're currently working on is somewhat integrated, but not fully, is we're considering pollen data as well, let's say in the more humid areas where, Here, there's a particularity. Pollen usually tends to build up over time, or the soiling that it creates tends to build up over time, which makes it a little bit more tricky to model. What we're doing in this here is we assume that we're talking about the early years of the power plant, therefore excluding, let's say, the more long-term effects of this kind of soiling. And then there are some kind of local sources of soiling, like agriculture, industry, a mine maybe. It is possible to include those as well, but of course, in this, let's say, high-level approach of simply calling an API for a location, they are excluded and are not taken into consideration. So you have to be careful. For example, if you know that you're putting a project next to a mine, this satellite concentration might not be representative of your location. However, it is if you are at the location which is fairly similar to what you would find in the entire region or a few kilometers around. Right. So now we have the particle concentration, and so next very important data set we're using is rain data. So as input source here, we use a combination of satellite data from a NASA satellite program, and we combine this with data from the closest weather stations. So for the hypothetical location of our project that we're looking here at the example, we see the 10 closest weather stations from the NOAA network, which data is included to form the above data set, which is the assumed historic data or rain that our target location has seen. So every green line in this heat map, every vertical green line represents one rain event in the past. And here's something. So, okay, and you can see already from the distribution that from January to March, you have few rains. From April to June, you typically have none. And then from July to September, you have a lot. And one thing is important for me to mention is that we do not work with a typical meteorological year or a typical rain year, but we work with the actual historic years to preserve the patterns that may arise. So because there are years that might be a little bit drier, where, for example, it did not rain all through February till July, and in another year you have in May you have a heavy rain, and that of course has a strong influence on the soil. So we do take this into consideration. Right, next step. So with combining these two data sets, what we can do now is we can get a soiling profile for the past 20 years. Here we see an example of 2017, showing the soiling level in percent. We see that the rain in this location, because it's mostly dust and very dry, is able to quite effectively clean the modules. But once it is dry, or once it doesn't rain anymore, the soiling builds up. Soil builds up over time, reaching in this year, for example, just before the rainy season starts and in the beginning of July, 8 or nearly 9% of soiling. Of course, here the rain patterns, of course, play a big role. So just to relate the two graphs together, so that below, here the vertical dashed lines are the rains of the respective line in the rain pattern plot. Right, actually, so this was a simplification. What's happening, showing you the results. What is actually happening in the background is a little bit more, is a process that is composed of a few more steps. So in our model, first thing we do is we calculate the mass deposition rate. So the particles suspended in the atmosphere, depending on the tilt angle or changing tilt angle over time. So if it's a tracker, that angle, of course, changes over the course of the day and at night. Therefore, we need the night stow angle and the humidity and some other factors. We calculate the particle deposition rate. Then we keep track on the accumulation of particles on the surface of the glass. That here, very important, here's where the precipitation comes in, which is able to wash away part of this soiling, as well as wind and other factors. As a next step, we then calculate which part of the incoming irradiation is shaded from the soiling. This is a function of the optical properties of the particles. And that then ultimately allows us to calculate the soiling level. Something that I would like to highlight here is a lot of the soiling models that are popular, they start with the soiling rate. We get often used, what kind of soiling rate do we use as an input? The answer to this is we don't have a soiling rate input. Actually, it is something that you could calculate from our soiling level as the rate of change or derivative of that soiling level curve. All right, so back to the soiling level. How to turn this into now the P50 loss factors. So again, let's look at the soiling profile for 2017. Oops, wrong button. All right. What we can do now is we can build monthly averages. And then what we do is we, of course, we not only simulate 2017, but we simulate all years from 2000, 2023 or 24, and create a box plot with the average values for each month. So how to read this? If you look at the box plot for the month of June, it basically tells you that in the data set, there is at least 1 year where the average soiling level in June was just above 1%. There's another year where it was nearly 13%, and the median value is 6%. So this median value is then what we, what the API really calls is the P50 or median values of that box plot. And this is what is passed back through the API, and that is used then in your yield estimation. One thing that I would like to point out here is, let's say, getting back to the alternatives that I mentioned in one of the earlier slides of a soiling measurement. Just imagine you had measured soiling for that location. It might have happened, but like in a likely scenario, your soiling measurement was for one of the years and falls right into that, let's say, statistical distribution towards the 6% in June. But if you're unlucky, you might have measured in just that 1 year where in June and maybe even May, it shows very low soiling. So you might be underestimating the later losses. Or the other way around, you just happen to measure in the year where there's very dry, and a lot of soiling, a lot of dust in the atmosphere, therefore overestimating the soiling losses. Through this, let's say, historical analysis, we're able to get a good average value and also account for, let's say, the year-on-year variation. Right, so this concludes the first part. This shows you so whenever you click now, or if you're a PlantPredict user and you hit the import PVRADAR button, this is what's going to happen automatically on our server. Now, so in the next part, now the question is, of course, like, okay, we're building this power plant, so back to my role as project developer of this project. And I have to now calculate with soiling losses of nearly 6% in June or July. And I might be saying, okay, this is a bit much. This is too much. I would like to reduce this. So one way of doing this, of course, is through cleaning. So here we see the effect of an instantaneous cleaning on the 1st of May. And this not only brings down the soiling level and therefore the P50 values. Basically, so what it does, it makes us leave the red curve and brings us on the blue curve. The benefit of that cleaning, the value of that cleaning is now equivalent to the area between the two curves. To the left, limited by the date of the cleaning, to the right, the first rain. So that area between the curves times the production in that period times the energy sales price. So that value has to pay for the cleaning and hopefully have a benefit above that. So here, in this example, we assume that the cleaning is instantaneous. That, of course, is usually not the case, especially for bigger projects. So our model also includes what if the cleaning isn't performed instantaneous, but actually over the course of 21 days. That has an interesting effect of the soiling level then never reaching zero, because if you have the first module will already see 21 days of soiling once you finish with the last one. Okay, so this is an example how the simulation works. This is the effects of the cleaning on the soiling level. But of course, as next step, to draw conclusions from that, and what we need to do for the optimization is we first have to translate that into actual energy losses. I was hinting at that already. So in the background, our platform also runs a yield estimation model for a simplified layout of that plant at that location. And then what it gives you is this kind of this plot showing the energy produced for each day of the year in green so that would be the yield if you would never clean. I can zoom in a little and get rid of that green part. What I see now is just a zoomed in version of the soiling losses in red and the cleaning gains in blue. You might be noticing that there are two different shaded reds and blue, and that is because we distinguish between what we call effective gains and losses and virtual gains and losses. Virtual losses being those soiling losses that actually do not show at the grid connection point because they are masked with curtailment, bi-curtailment, or clipping, inverter clipping. So our model do take into consideration that as well. And with higher DC-AC ratios, you will find that less cleaning is actually needed, as much of that potential soiling is not really passed through to the grid connection. All right. So now we have the energy gains and losses. Right. All of what I showed you was the example of this hypothetical cleaning in 1st of May. Our web application allows you to, well, you can define manual cleaning strategies, saying I want to clean every year at 1st of May. But what you can also do is simply tell the program, my options that I would like to consider for this power plant are manual cleaning. There are options fully autonomous robots, tractors, or semi-autonomous robots. There's an entire database of systems that you can use. You can use our versions, or you can create your own in your private database. And what is being modeled in the background is a technical system composed out of, let's say you're thinking about using a tractor. So that tractor has a speed, a consumption that needs personnel. It has components that might have to be replaced after some time. So all of that is considered. And it can be paired with a business model where in one example, you would like to share, what if I use that machine as a service? So I just pay a per cleaning fee. Or what if I buy it myself? And then, of course, there's purchase cost and replacement cost that you have to cover. So this is it's all possible to represent that accurately. Here we see, so let's assume we chose one of these cleaning packages. Then the system will automatically find the optimal cleaning dates for each of the historic years as your best guess for how often, so it will automatically find the optimal cleaning times for the past 20 years, and then use that as a base case for your future scenario, assuming that the next 20 years will roughly be show the same pattern as the last 20 years. What you notice is that from this cash flow, you can already see that there are years which are fairly average, where one single cleaning is enough or is the cost optimal. But then there are other years which is a lot drier and where actually 3 cleanings are needed for a cost optimum. And there may even be years, although it's just one, where there was sufficient rain and 0 cleanings are needed. At this point in time of my project development, I could use this information to say, all right, my base case will be 1 cleaning a year, and this is what I put in my cost estimation and in my budget. Right. Okay. So this brings us back to the soiling loss factors. Just to, let's say, close the loop. We have started, so the result of the first part of the presentation was what the API sends back, and that is the soiling level, assuming no cleaning, assuming earlier years of production, based on historic data, and that gives you, that might give you values, or in this case, gives you values in June, a median P50 value of 6%. And then through the platform, what you would then get is the soiling level and P50 soiling levels, assuming that optimal cleaning strategy. And as you can see, in this case, our average or median soiling loss in June has been dropped to just 2%, and the global average has dropped from 2.28 to 1.26%, which of course is a benefit for our yield estimation. Just the last slide on showing how the platform looks like. So this is the user interface showing the results of our cleaning optimization. You see a graph showing the above graph, the top graph shows the total cost of ownership of the different cleaning solutions that have been compared. You see on the right, no cleaning. If you in this example power plant, if you decided to never clean, then you would have to assume losses worth 18 million euros over the entire lifetime of this power plant. However, it is possible by choosing an optimal cleaning strategy to reduce this total cost of ownership to roughly half, therefore reducing the soiling losses by 50% through a regular cleaning. In this case, the optimum that has been found is a dry cleaning tractor as a service. Our platform then lets you do that. You can jump into details, basically see all the graphs that have been shown previously. It also lets you print reports that you might want to add to your project documentation. All right, enough of the platform. Let's go back to the models. There's one point, of course, that comes up pretty much every time. And that is very important, of course, and that is model validation. So this is all nice. It all looks very nice, but of course, it only works if the models produce precise results. At this point, I would like to mention that model validation is really important to us and is something where we spend a good amount of our time that we spend developing PVRADAR. Here, what we're doing in the background is we're building a database full of available soiling measurements. This can be from publications, from our scientific partners. So we use that database to improve our internal processes, but also to, let's say, fine-tune model parameters for different climatic zones. So here I would like to give you an example of some of that data in that database. And this is actually data that is publicly available. It's on the Duramat platform. You can find the link on our website. So that in 2017, there was a paper that came along with 10 data sets from measurement campaigns from NREL at different locations in California and Arizona. And let's look at one of the let's have a look at one of the projects in Kern County, actually in the north of California. What we see here is the comparison of so in red, we see the soiling measurements that have been published in the paper. And on top of this, we see our modeling, the result of our model. As we can see, we have a very good fit for, let's say, most of the dry period, although of course there are always some local differences. However, what happens is that it seems to, and just to be very transparent, no model is perfect, nor is ours. In 2014, in spring, it looks like that our model is actually a little bit underestimating what is going on site. And we have what we assume is happening here is that there is, because it's springtime, there is some pollen in the air, in the atmosphere, which is not yet accurately represented in our models, or not to the full extent. So this is something where we're working on trying to improve these models. Nonetheless, I just would like to, just to show you how good this fit actually is, what I would like to also show you is compare that to the results of popular models in the PVLib library that probably are familiar to most of you. And I'm speaking, of course, of the Kimber and HSU model. So in this plot, I have added these models for the same location using their default parameters that are provided in the library and in the papers that come with it. So it might be the best guess if you were to use them. And what we can see is that our model is not only a lot better than these two. So if you were to use, in this case, PVLib HSU, you tend to underestimate soiling, at least at this location, and the Kimber model tends to overestimate the soiling, which is mainly because of their rain cleaning threshold. In terms of modeling error, we can see that our modeling, our error is far smaller. Actually, if we do the same for all of the 10 sites that are in this data set, we find that we have a 35% lower root mean square error compared to the best option in PVLib, which is the HSU model across the 10 Duramat sites. And if you want to look at this very data, we have interactive graphs on our website showing this very graph and all the other graphs for the other 9 locations. And you can find that if you visit pvradar.com, and on the first page, there's a link to that page. Okay, with that, I would like to come to conclusions. So what I hope I did over the past 20 minutes was show you that there are several advantages of modeling soiling based on physical models and historic data. Them being that they maintain that they maintain climate-related patterns and therefore account for the variation from year to year and the different seasons. Our model is research-based, so in that sense, that helps making it more robust and reliable. It is validated against real data, leading to precise results. Again, no model is perfect, and there will certainly be areas where our model still needs some improvement, but we're constantly working on fine-tuning the parameters just a little bit more to get a better result. And I think the biggest, let's say, drawback of our models, or any model actually, is when, and what users might have to be careful about, is when you are looking at the site that is close to a very strong source of pollution that is not represented in the data sets that we have. That might be, for example, close to a mine or quarry or unpaved road, which you know that every time a construction site, for example, during the construction of the power plant, that construction dust is of course not part, right? But it is possible because there is a physical model, so they have model parameters that can be tweaked to better take this into consideration and create scenarios. And then relating to the poll question number 2, so I hope I also showed you that there are advantages of making soiling part of the design process or even of the development process of the power plant and start using it very early. The reasons for this is that it helps you reduce the risk of underperformance. Therefore, in other words, to help you to avoid surprises in later years. It helps you to allocate cost-effective cleaning budget. What I noticed in my personal experience is sometimes for some projects, it's very difficult. So once the financial close of the project is done, and maybe you said, okay, well, we assume 2% and we say 0 cleaning budget. Once the power plant is built and the budgets are defined, it's very difficult to change that, even if you can prove or you see that cleaning is needed, at least in my experience. So it makes sense to put this into the budget early on. And then also it helps you to, once you know that you need cleaning and which machine you will be using, you can pass it on to your APC and tell them, look, we need a machine to drive through these roads, so please avoid any obstacles. Yeah, this sounds easy or simple, but in more cases than you would believe, there are combiner boxes in the way, making it significantly increasing the distance that cleaning machines have to travel, and therefore increasing the cost. And you can, of course, avoid that by starting to think about this early. Right. And with that, right, I come to the end of my presentation. And maybe let's kick off the Q&A session with a third poll question. And that question would be, when do you typically invest in determining a cleaning strategy and the associated soiling losses? So in which phase of the project? Okay, I don't know if this is now influenced by what I've just been saying, but I tend to agree with the responses now a lot more than with the second poll question, tending to like having a favor for, let's say, the development phase and the detailed engineering. Jason, with that, I think I will give it back to you.
Yeah, great. Actually, if you want to, yeah, you can give it back to me, or if you want to keep driving, there's only a few more slides left. I can walk you through it.
Let's see. Sorry, maybe you take over again.
All right. So I'll share a screen, and okay. So everybody should be able to see my screen at this point. So, so thanks, Thor. That was awesome. Really good technical topic, and I can already see by the questions that are coming in for the Q&A session that people were pretty engaged. So, but before we get to the Q&A, and as we kind of start to wrap up the webinar, I wanted to make an important announcement. Our next major PlantPredict release, version 12, is happening next week, September 5th. This will initially be released as a beta version, which is customary for all new PlantPredict major releases. And the primary feature will be a new site-level 3D shade analysis. And I've included a few screenshots here. this has been well over a year of development, and we're so excited to get this into the hands of all of you guys and all of our users. And so this has been a long time coming. Initially, you'll be able to import PV Colada PVC files into PlantPredict to define that 3D scene. And as many of you know, 3D shade modeling can be extremely resource intensive. And that's why we're deploying a whole new host of cloud servers dedicated to just the shade modeling portion of the prediction. So this means that the 3D shade processing isn't limited by and isn't going to be tying up your personal PC hardware. We've also got a few other notable features included in version 12, including a new integration with array technologies. In some ways, it's kind of a similar sort of API integration as what we just talked about regarding PVRADAR. But basically, it's going to allow predictions to retrieve tracker rotation angles directly from ATI using ATI's proprietary tracker control algorithm for irradiance optimized backtracking. So this is really an exciting integration because we're starting to bring the model, closer to how the installed system will actually behave. So it's notable. Okay, next slide. Closing notes. So speaking of version 12, look out for our next webinar. It's going to be on September 25th. My colleague, Kurt Ree, is going to be leading that webinar, and we'll be really giving a deep dive on the 3D shade modeling, as well as more of an overview of the version 12 features. Finally, if you're planning to attend RA Plus in 2 weeks, please stop by and say hi. I'll be there along with a number of my PlantPredict colleagues. We'll have several demo stations dedicated to just the PlantPredict suite of products. And we'll also have team members representing our other products, Construct, Terafab, SCADA, booth D27001. And we'll definitely be showing off version 12 and the 3D shade modeling at RA Plus. So with that, I'll hand it back to Thor to give some closing remarks on PVRADAR, and then we'll head into Q&A.
Yeah, thank you, Jason. So at this point, the only thing I would like to mention is that if you, well, of course, if you're a PlantPredict user, please start using that API, test it out. If you have any feedback, we're always happy to hear from you. Also, if you have any questions, we're very open to answering those questions. Also, of course, if you would like to have any more information about our other products, you see our email addresses on screen. Please, we're very happy to hear from you and help you solve the kind of problems you're having, even if they mean a little bit of tweaking of what we have. There's also, unfortunately, we will not be at the RE Plus this year. However, for those of you who are going to UPVSec in Vienna in September, my colleague Franco Clandestino will be there with 2 poster presentations, and please reach out to him for, let's say, a live demo or just to meet up and have some questions. And of course, if you're interested, let's say, to extending the use of the API, giving you results for uncleaned or soiling losses, assuming no cleaning by, let's say, an optimal cleaning strategy. What we're offering is a trial. So please contact us and ask for a trial or validation project. I think this is the best way of showing you, let's say, the value of it and how to include that in your processes. And thank you for attending.
All right, so that brings us to Q&A, and we got just about 10 minutes left, which is perfect timing. So I will kick off some questions, and we've got quite a few. And just a reminder that anything we don't get to, we will definitely respond to in writing to whoever submitted it. So feel free to continue to submit questions, even if we're getting towards the end of time. So first question, there's a couple about this. Does PVRADAR data cost anything? And so the PVRADAR integration within PlantPredict does not cost anything. So there's no increase in the PlantPredict pricing in order to access that data. And right now, currently, the PVRADAR feature is accessible across any tier of our product. We're probably going to be moving that in the near future to be accessible only to our priced tiers. But for as of right now, it is across all of our PlantPredict products, and yeah, the data itself is not going to cost anything to PlantPredict users. Um, so um, next question. Is this data worldwide or US only? So good question. I don't know if we mentioned this specifically, but the PlantPredict integration currently, so the API integration with PVRADAR is only for the US currently. Tor and I have been talking about extending that beyond the US. This is really just a sort of a first step integration. So I do expect us to expand beyond just the US into a more global coverage. And I don't know, Tor, if you want to mention anything about sort of from your side.
Yes, so true for the integration. The API that we integrate into PlantPredict is limited to locations in the US, mainland US actually, so excluding Hawaii, for example. But yes, we have data. So we have data for the entire for locations worldwide. So if you have a project outside the US, feel free to contact us. It is possible to use to get soiling estimations and optimize screening strategies for these locations as well, just not through PlantPredict at this point in time.
Yeah, thanks. And it's also worth mentioning that, the PV radar model integration is really the first of several models that PlantPredict would like to integrate. So we are talking to others about similar integrations. Okay, next question. Is there any integration of cleaning soiling within PlantPredict? So currently, no. The PlantPredict integration is purely a uncleaned soiling loss value. You would, basically go directly to PVRADAR if you're interested in sort of that cleaning analysis and what the change in loss factors would be. Anything you want to add there, Tor?
Exactly. Yeah, this is the current approach. And so this is what you currently would have to do. Of course, if you have a project, for example, we saw that project in Florida, and then yes, you might say, okay, so cleaning is not a major concern for this project, so I don't need this. But of course, for the other example that you've shown in California, this might be a good idea to see, as I've shown in my example, Arizona, that there is actually value. So depending on the project and what kind of values are returned by the API, you can take a decision on this, whether it makes sense for your project. And then contact us, and we can give you access to the PVRADAR platform, which is not free, but we have convenient offers.
Great, thanks. And then next question, there's actually a couple of questions that are semi-related, so I'm going to combine maybe a couple of questions into one. But the question is, does this mean that soiling measurements on site are no longer needed? I guess this means like sort of a pre-construction soiling measurement campaign. But on a related note, if you were to conduct soiling measurements on site, is there a way to tune the PVRADAR results? So do you want to take that one, Tor?
Yeah, I do. Great question. Yeah. So let's say if I was developing projects, so I would of course use PVRADAR first. My answer, so the first answer, is it needed to make soiling measurements? And the answer to this depends on the site, I would say. If you have a site that is, I mentioned this throughout my presentation, you have a site where you could assume that, for example, we see here this open plane and you build a power plant in the middle of it in this very image, you can assume that in that plane, the soiling conditions will be fairly equal. Therefore, our estimates will be rather good, will be very good. If, however, you have now a dusty road, where this is just coming from a dusty road or a mine, and you're just building this right next to that mine, in that sense, then I would recommend building using or going for a preliminary or pre-construction soiling measurement campaign. And to answer the second question, yes, it is possible to fine-tune model parameters based on these measurements. So what we would do is we can, as we showed in the presentation, we can compare the measurements against our models and then see if we can tweak some of the model parameters to get a better fit and then use that model to run on the entire historic data set, as well use as a means to predict the soiling for the next year. And that should give you better results. In that way, that measurement that you might have is a way to include, let's say, more localized effects into your prediction. And if you have such a case, again, please reach out. This might be a great validation project and to see and for us learning, yeah, how to improve.
Great, thanks. A lot of good questions here. Next question is super easy. Will we be getting a copy of this recording? Yes, absolutely. We typically send out the recording to all attendees within, I think within 48 hours, but it generally comes out pretty quick. Next question, will PlantPredict version 12 come with a price increase? So initially, no. So basically the version 12 beta will be available at no additional cost. So you'll be able to run 3D shade models at no additional cost. We are spinning up quite a bit of additional cost for the processing compute times for these shade models. So we're going to be, taking a look at that over the next, couple of months or so, and we may be rethinking some of the pricing going into next year. But over the, probably for the remainder of this year, I don't expect any price increases. Okay. So next question. Can you confirm that PVRADAR soiling loss estimates do not include snow soiling losses? Tor, you want to take that one?
So can you repeat this?
Can you confirm that PVRADAR soiling loss estimates do not include snow soiling losses?
Yes. So, well, depends. So the API is based mainly on dust soiling and or ignores snow soiling. We are working on, or we have a solution that, so basically with PVRADAR, what you can do is you can get access to snowfall data and then run PVLib models, Marion and Townsend. As if these are not our models, we do not include them automatically, as we do not know which of, well, we haven't validated them ourselves, as there's just very little validation data available for snow models in general. We hope that this changes in the future and that we can add, let's say, our own validated snow model just on top of the standard soiling model and give you the combined losses. It is possible to do that with PVRADAR. However, you would have to choose yourself which model you use and which modeling parameters you want to use, because we don't have the data to, let's say, to say, well, these results are correct. So yeah, currently not included.
Great. Okay, that takes us to time. I'm gonna call the webinar here, and I just want to say thank you everyone for attending. We've got a huge amount of questions, and we're going to do our best to answer those over the next few days and send these out to the people who answered them, or who asked them. So Thor, thanks so much for presenting. It was great, and appreciate everybody for attending today. Hopefully it was informative.
Yeah, thank you, Jason. It was a pleasure. It was a very nice experience.
Great. Okay. Thank you, everyone. Bye.